Alright, we got our review for Q110. This is a Saturn Titan system. We'll begin with the scientist chart. So remember, I've mixed up the order and I've given you one thing in each row. So if we look here, we see the relationship, the inverse square relationship. So that name would be Newton, and he would be number 3. 6, that was Einstein, and he said that mass warps space-time. 4 is Cavendish. Cavendish turned what Newton said and turned it into an equation. He did that with his big G constant, which is 6.670 negative 11 Newton times meter squared over kilogram squared. Number 5 was Einstein again. He said moving clocks run slow. 2, Kepler. Elliptical orbits. When it's closer, it's going faster. When it's further away, it's going slower. Equal area and equal time periods. So this is equal to that in terms of area for the time period of 1 month. 1 is Copernicus, and he had the sun-centered or heliocentric model. You'll want to practice that before you get to the quiz, because it can be a little harder than you think. Moving on to the mass-weight chart. Mass is the same everywhere in the solar system. To find our weight on both Saturn and Titan, we're going to use this equation right here. Big G, little m, big M divided by d squared. In both situations, 75 will be little m, and big G will be 6.670 negative 11. And then we'll have to take information about Saturn. So the big M and little m, or big M and little m. If we're talking about Saturn, we'll use the distance between, which will be 60.3 e to the 6. If we're talking about Titan, we'll use the distance between 2.575 e to the 6th. And then we'll use the mass of Saturn, 5.769 e to the 26, and we'll use the mass of Titan, which is 1.35 e to the 23. All this came from up here at the top if we look at the system. So, plug it into this equation right here. Let me slide everything up a bit. So we have 6.67 e negative 11, and we're going to multiply that times the little mass, which is the person, times, let's do Saturn first since it comes in our chart first. Saturn had 5.69 e to the 26 for its large mass, and then I divide by the distance squared. So the distance would be the radius, 60.3 e to the 6th squared. And you can see the weight on Saturn is 782, which is a little bit more than Earth, 0.8. And if we divide by 75, we get 10.4 for the gravity constant. Go through a similar process for Titan. So we leave 75 in here, and we get rid of the other mass, and we turn it into Titan's mass. Titan's mass was 1.35 e to the 23. And then we divide by the radius squared, which was 2.575 e to the 6th squared. And we get only 101.8. And then we divide that by 75, and we get our gravity constant, 1.35 meters per second squared, which is pretty low, but Titan's not very big. So that's how we do this chart here at the top. Sorry. Now, we have a question here. Which one pulls in the other one more? So this is Newton's third law, action, reaction, equal and opposite. So the answer is the same, of course, right? If you look up here, you can see these arrows that represent force of gravity, and they're identical. So this force is equal to this force. Now, if we want to solve for that force, we're going to use Newton's law of universal gravitation again. But this time, the big M, little m, and d squared has changed. So we had to adjust accordingly. and we still use 6.67 e negative 11, and we'll make the little mass Titan this time. Not that it really matters who you make big M and who you make little m, you'll still get the same answer. And we multiply that times Saturn, 5.69 e to the 26th, and we would divide all that by the distance between 1.22 e9, the radius of the orbit. Remember, d and r, that's our big problem, is keeping those things, realizing they're both distance, d or r. So now we plug it into our calculator. So I had 6.67 e to the negative 11, and then I had 1.35 e to the 23, and then I had 5.69 e to the 26, and then I divide by 1.22 e to the 9 squared. And you can see I get 3.4 e to the 21, which would make sense because it takes a lot of force to keep something like a moon in its orbit. So 3.4 e to the 21 is what you get. Let me get my key here real quick, hold on. I had a different number written down in my key. So let me just double check everything here. We had 6.67, 1.35 e to the 23, 5.69 e to the 26. Had that right. 1.22 e to the 9 squared. Well, we'll just go with it. 3.44 e to the 20. No, that's what I had. Duh. Sorry about that. Alright, so now we're ready to calculate the velocity of Titan. Remember, there's more than one way to calculate velocity. So we can do velocity that has no rounding error, which is based on big G, the center mass, then divided by the radius of the orbit. So I can put in 6.67 e negative 11. I could put in the center mass, 5.7 e to the 26. I can put in the radius of the orbit, 1.22 e to the 9. So I can plug it in like that and see what I get for a velocity. So let's do that. So we have the, well, I'll do square root here at the end. So I have big G, 6.67 e negative 11. I have 5.7 e to the 26. I have 1.22 e to the 9. And then I want to square root all that. And you can see I get 5,582. So then let's see what we get for if we use the other equation. Meters per second, of course. We can also find the orbit velocity by using square root of f grav times the radius of the orbit divided by little m. So that would look something like this. We'd take our previous answer, which we rounded, so this isn't as good of an answer, 3.4 e to the 21, multiply by the radius of the orbit, 1.22 e to the 9, and then I will divide by the outside mass, which is Titan's mass, 1.35 e to the 23. And then I have to square root all that. So let's see what that looks like when we do it in the calculator. 3.4 e21 times 1.22 e to the 9 divided by 1.35 e to the 23, and then I want to square root all that, and I get 5,543. So it's pretty close, but not identical. It's close enough to know that our f grav answer is now right, and our velocity was good enough. But if we have to pick one, we want to use the one that had less rounding in it. Looks like that. Okay, calculating orbital time in Earth days. So to do this, once again, we have two options once again. So one option we could use would be using big G, which is probably the better option. So t equals 2 pi times the square root of r cubed over big G times m. So that looks something like this. Remember, when you do this work, you have to be careful about 2 pi. It can be tricky sometimes. 1.22 e to the 9 is the radius of the orbit. Remember, it's the orbit radius that we're cubing, not the planet or the moon. Big G is 6.67 e negative 11. The Saturn's mass would be 5.7 e to the 26th. And that will give us the time. So we get something that looks like this. We'll do everything in the square root first. So we'll hit 1.22 e to the 9, and then we'll cube that, and we'll divide by big G. Then I'll divide by 5.7 e to the 26, and I'll square root it all, and then I'll multiply by quantity 2 pi. And I get this incredibly large number of seconds. So I'll write that out, 1373154.07. Now, what I want to do is I want to go to my unit converter and convert that into days. We go apps, up to side tools. Once we're in side tools, we want to go to unit converter. Once we're in unit converter, we want to go to time, so 4. And we want to put in this number, 1373154.07. 1373154.07. That number of seconds we want to turn into days. And when we do, we get 15.9 Earth days. 15.89 or 15.9 Earth days. So basically 16 days for Earth days for Titan to go around Saturn. Then we get to we can also prove this time by doing it with the other equation. Almost forgot. So T can also be found by doing 2 pi times R divided by V. So we could take 2 pi, we could multiply it by 1.22 e to the 9, and then we could divide by our best V, which we said was 5,582. Remember, this is going to have a rounding error in it, but it will give us a good approximation for our seconds that we wrote down earlier. So we'll see if we did it right. I almost forgot about checking myself. Can't believe that. So then we multiply 1.22 e to the 9, and we divide by the speed, 5,582, and we get pretty much the same number of seconds. This is what we had last time, 1373154. 1373250. We knew it wasn't going to be exact, but it's close enough for us to know we did our time right as well. So we have all these ways of checking ourselves, which you want to take advantage of. What would happen to the force between the moon and the planet if the mass of the planet is halved and the distance is halved? So we look at our force equation. Now we don't want to use the big numbers, right? We want to keep everything simple. So we start by saying, okay, if everything was 1, we would get 1. If the mass of the planet is halved. So the planet would be big M. So we'll make that 1/2, and the distance is halved. So we make this a half squared or a quarter. So we end up with 1 times 1/2 over 1/4, or 4 over 2, or 2 times as much. So we end up with twice mass of the planet is halved, the distance is halved, so it would be a quarter. Would take us up to 4/2 or 2. Yeah, I think it's 2. My key I have 4 though. Well, I'll have to look at that. We'll say 2 for now, and then I'll adjust it in class if I need to. I think I did it right. I'll just think about it a little bit more. Well, there's a way to check yourself here with this last part, which is the velocity. So one way to get velocity would be to do the square root big G times the center mass divided by R. And since we had a half this and half this, what happens to force and tangent if the distance is halved? Okay, so we get the square root of 1. Square root of 1. Make sure I wrote this right. Yeah, that would be right. Square root of 1 is 1, right? So it would kind of cancel itself out. So I'll check those because I'm just not feeling all that strong about those, and then we should be good to go.